Okay, thank you. Thank you very much for the invitation. I would have really liked to come back to India once again, but okay, things are what they are right now. So I hope that, in one of the next opportunities and next schools, I could come even maybe to give a talk or something and share some real time with you. Okay, so let me tell you about the way in which I thought about these lectures. Um, my idea is not to be so technical. I know there are going to be other lectures in this same school, which will, be much more technical than mine, and there will be developments of calculations and things like this. I thought I was going to give, since I'm also the first one, going to give more of a generic view of which are the kind of problems that are open and on which many of us are working presently, and so give you some kind of vision of what's the situation concerning out of equilibrium dynamics of complex systems. Okay, I am going to do it with slides. For some reason my tablet is not connecting to the Wi-Fi today, so from tomorrow I guess I'm going to use the tablet, and I will be able to write on top of the PDF at the same time as I speak, but today unfortunately I cannot do it. So I hope that at least with this pointer I can show you and try to make it a little bit more easier to follow. So I mixed a number of old transparencies and prepared new ones, and I already see that there is a mistake in the very first one. So my affiliation here is changed a little bit. So now, there were mergings of universities, change of names in France. So now it's back to the old times of being called Sorbonne University. Just just the first line is the name of the university where we all work. Even Greg is in my lab right now as well. So anyway, so this is about the kind of introduction. As Abhishek was saying, please feel free to stop me anytime with questions. Every, I don't know, 15 minutes or so, I will make a break, and then you can ask all the questions in the chat. But if you have urgent questions, don't hesitate to stop me while I'm talking. So I have 5 lectures. I thought I was going to focus on 5 different subjects in each of these lectures. So depending on how I go with time, I will be able to cover all of them, or maybe just the first 4. There's something about the video. I don't know if this is okay or not. Okay, so today is going to be an introduction. So I want to tell you a little bit about the 4 subjects that follow, but in a kind of descriptive way. And then from tomorrow I will get a little bit more into the details, although as I said, I'm not going to be very technical. So the 4 fields I'm going to talk about are coarsening, domain growth, topological defect, erasure during evolution, when you take a system across a phase transition. I'm going to let you know a little bit about the special features of problems which quench randomness or disorder. Then I'm going to talk about active matter, which is a very active field of research right now, has to do with models which are biologically motivated, but in the end, they're statistical physics models that we try to understand with physical techniques. And then if I have time, I will tell you about problems which also belong to the area of statistical physics, but which are motivated by experiments and calculations in quantum situations, especially in the context of atomic physics, where people are able to study systems of atoms, for example, in quite good isolation from the environment, and especially they can study systems of atoms which are very close to being integrable systems. So all the special properties of integrability arise in the calculations, but also in the fundamental questions that one can ask about equilibration or not after long-term evolution of these kind of systems. So these are the 4 main topics I want to cover in some descriptive, a little bit technical, but not so much way in my talks. Okay, so let me start with my first lecture here. This is the plan of my lecture. So I'm going to start from the very basics and discuss a little bit about what is equilibrium and what are the differences with systems which are not able to reach equilibrium and that they evolve in out of equilibrium situations. I insist upon classical because, of course, as I said, nowadays there's a lot of activity around quantum problems. The questions are very similar, but there are some specificities about the quantum mechanics in them. I'm not going to tell you much about quantum mechanics apart from the motivations for studying integrable systems. Then I'm going to tell you about how can a system stay far away from equilibrium for all the measurable times in an experiment or a numerical simulation. And I will go from the very simple, which is just a single particle situation, to a many-body one, given some examples, and introducing the examples on which I will develop the 4 lectures. And finally, I will finish today with some kind of conclusions and purposes. So what do we want to do with these systems? I mean, what kind of questions we want to try to answer, and with which kind of methods. Okay, so let me start from equilibrium versus out of equilibrium. So you know that the big advantage of statistical physics is that you don't need to solve all the Newton equations, say, for a system of n interacting particles to say something about the global behavior of this system after some equilibration time. Of course, it's very difficult to know what is this equilibration time as a function of the parameters in the system in question, but basically one assumes, and this is the content of the ergodic hypothesis, you assume that there is some equilibration time after which the macroscopic observables of your system can be, on average, obtained with a static calculation, so there is no time involved in this calculation, as an average over all configurations in phase space. So imagine you have a system made of particles, so you have the positions and the momenta of those particles, and this ensemble of n 3-dimensional or d-dimensional vectors times 2 because of the x's and the p's constitutes the phase space of the problem. So you average over all the configurations in this phase space, weighted with some probability distribution, which I'm calling capital P here, and you compute this integral of the observable of your choice, let's call it A, and then this characterizes the properties of this observable, which, if it's not ill-defined or very special or typical, generic, and well-behaved observables, you can compute this static average, compare it to the temporal average that you could calculate with an integral over time of this observable measured at on the trajectories of your system in the phase space and normalized by the length of the time window over which you're averaging. And these two kinds of ways of measuring the observable average should coincide. So statistical and temporal averages should coincide. So what is done in an experiment typically is to follow the evolution in time of your system, and the experimentalist measures the time average. While this is typically very difficult to calculate analytically, so we theoretical physicists, we use the statistical physics formalism or framework and this hypothesis, and we compute the statistical average, which is the one which is in this equation above. And of course, this is the development of statistical mechanics starting from Boltzmann by the end of 19th century. So there's no need to solve the dynamic equations. What are these probability distributions? Well, it depends on the conditions under which you look at your problem. So if the system is isolated from the rest of the world, well, you know that it's the microcanonical distribution, the one that describes the statistical properties of your system. In this microcanonical distribution, all configurations in phase space are equally probable. And then the probability distribution apart from a normalization, is a delta function of the quantities which are conserved by the dynamic evolution. So if it's only the energy which is conserved, then it's a delta of the Hamiltonian of your problem minus the energy. But if you have more, I don't know, angular momentum or something like that, then you also have to impose the conservation of those and extend a little bit your microcanonical distribution to have other delta functions. But okay, apart from these little differences, in normal situations, you have a few delta functions that define your microcanonical distribution and equal probability of configurations in the accessible subspace of phase space that your system will visit during the dynamics. So for example, here I'm just saying that the energy is conserved. So E is the value of the energy that you fix with your initial conditions, then it's conserved along the evolution. And, within microcanonical distribution or microcanonical setting, you can define an entropy, you can define a temperature, and okay, these relations that characterize the, again, microscopic properties of your problem. If your system is not isolated from the rest of the world, and for example, you can exchange energy with the environment, you know that the idea is that from the whole world which is isolated, you select a piece, you focus on that piece, which I'm calling in the sketch the system here. The rest is the environment. You have interaction between the two, and you exchange, for example, only energy between the two, not particles, let's say, just energy. And then the total energy is conserved, which means the energy of the system plus the energy of the environment plus the energy of the interaction. But if you neglect the interaction between system and environment, assuming short-range interactions between the two, if furthermore you say that the system's energy is much smaller than the one of the environment, because you assume that the system is small compared to the rest, then you can derive from the microcanonical distribution the canonical distribution, which takes this normal Boltzmann weights form with the exponential of minus beta h, with beta the inverse temperature of the environment, which is related to this object here in the microcanonical formulation. So two issues which are sometimes forgotten that have to be used in the derivation of the canonical from the microcanonical is this short-range interacting character of interactions between system and environment, and the fact that the system is much smaller than the environment. I'm insisting upon these two, and also upon the fact that you have to impose delta functions on the conservation laws that you have in your system when you construct the microcanonical distribution, because one of my topics, which is this integrable systems behavior and possible statistical description of them, will go beyond those, and they will be beyond in two ways. They will be going beyond because you will have to impose as many constants of motion as degrees of freedom you have in the problem. So you will have, for a system of n particles, you will have n delta functions to impose. So it's a bit weird, but okay, it can be done. And the other thing is that the concrete example, if I have time, that I would show you of an integrable system which is completely solvable and for which a statistical physics description can be derived, will be of a kind which violates this short-range interacting character, but still you can go and propose a microcanonical description for it and derive a canonical description for it as well. So, okay, this is just to recall certain assumptions that we usually do, sometimes without saying, when we talk about standard statistical physics, that will jump over them in more contemporary examples of interest. Okay, so statistical physics has been very successful in describing lots of experimental situations. It has been also successful in explaining some features of thermodynamics, which, for example, was a little bit, I don't know, mysterious as a theory, also very successful. But the macroscopic justification of thermodynamics comes from statistical physics, and the understanding and derivation of equations of states, like this PV equals NRET, the law of gases, perfect gases, is also, you can derive it with statistical physics, formalisms, and so on. And it has also helped a lot understanding collective effects, and we're going to talk a lot about collective effects, which give rise to phase transitions, of course. And, the understanding of phase diagrams, the understanding of the phases of those phase diagrams, the critical behavior when there's changes between phases, and so on and so forth. So statistical physics gives a framework to calculate objects. Of course, the calculations can be perhaps difficult to achieve until the end. As soon as you put, non-trivial interactions, it can be very difficult to do all the calculations by hand. But still, I mean, the framework is clear. The ideas which are behind, the assumptions which are behind, are also clear. And then it's a question of, math, if you wish. I'm not going to say much about quantum physics, but still, I just want to remind you that there is this mapping between classical and quantum in equilibrium that goes by basically going to a system with one more dimension, which is imaginary time dimension. So once you rewrite your quantum partition function in a convenient way, you realize that it's the classical partition function of a system with one more dimension. These are observations and results going back to Feynman and collaborators, but also Trocker and Suzuki in Japan, and Matsubara. And seen in this way, the quantum statistical physics is just classical statistical physics with some peculiarities, but again, at the level of the calculational tools, but not really at the level of the fundamental issues. So, you can have quantum phase transitions, you can have quantum Monte Carlo methods based on statistical physics ideas, and so on and so forth. So quantum statistical physics, from this point of view, is just classical statistical physics with some addendum of a little complication. Okay, so to go from dynamics to statistical mechanics, as I have discussed, you have to distinguish closed from open systems, but also you will see that you have to be a little bit careful about this assumption of reaching the conditions under which the equilibrium hypothesis can be assumed. So there are two ways in which the equilibrium hypothesis can fail. One is that this equilibration time can become too large and not reachable experimentally. And the other one can be that you focus on a system which is not really isolated and on which you have forces acting on it, which, for example, don't derive from a potential. So they are not, of the usual Newtonian kind, but they have special features that keep the system out of equilibrium because they inject energy continuously on the system on which you want to focus. And okay, I will, in the rest of the talk, give you several examples of these both situations, starting from the simple and going towards the complicated. Okay, so close out of equilibrium. I'm going back to the first part, the microcanonical discussion I made at the beginning. So there you can ask the questions, does the dynamic of a particular system reach really a flat distribution over the constant energy surface in phase space? Just here, focusing on just one conserved quantity, say that is the energy. And this kind of question belonged for a long while to the mathematical physics community, in a sense, because it was, the content of ergodic theory, and people were, we physicists, we sort of forgot about this issue and said, okay, let's assume that this applies and don't bother about proving that these hypothesis of reaching the flat distribution in the constant energy surface applies. But this has been sort of revived recently, as I said, in the context of the integrable problems, in the integrability. And this will be the theme of my fifth lecture. So, okay, I repeat this slide here, and it's the issue concerning when this first half of the slide is justified or not. But then, okay, most of the cases in classical statistical physics that we're interested in are not closed. Usually we have a problem in contact with the bath, with an environment, and we want to know whether the canonical distribution is reached by the problem at hand. So what is an open system? Okay, you focus on some problem, you have the surroundings, which is the environment, as I said already, your energy or your Hamiltonian, you can separate in pieces. One concerns the degrees of freedom that belong to the system on which you want to focus on. The other one concerns the degrees of freedom of the environment, and then there is the interaction between the two. And say that the dynamics are given by Newton equations. If you are quantum, you can focus on Heisenberg kind of evolution, for example. And the idea is that you integrate away the degrees of freedom of the environment, and you then derive what's going on for the system itself. Okay, so if you are under these conditions of your system coupled to environment, then you can go back to the mechanical point of view, and you can say, well, I will join all my phase space variables into this long vector with many components that includes the positions and the momenta of my particles. Then you choose an initial condition for your problem with some prescription, and you let the system evolve in time. And if you're an experimentalist or a numerical person, you measure. At a certain moment, you start measuring. Say that this moment, when you start measuring, we call it waiting time, because beforehand you haven't done anything on the system, you just let it evolve. And at waiting time, you start measuring. So you can measure over a length of time that goes from t waiting to some longer time t. Then, to be in conditions of equilibrium, this waiting time has to be longer than the equilibration time of your problem. But again, as I said, sometimes this is not possible to reach times which are longer than the equilibration time. Then, if you are in this second situation, when t waiting is shorter than the equilibration time, the system remains out of equilibrium, and you're not justified to use thermodynamic notions nor the Boltzmann weight for the to compute averages a la statistical mechanics. So to be in equilibrium, there are some conditions that have to be fulfilled. These are necessary but not sufficient conditions. But necessary conditions are that the bath itself should be in equilibrium. So I will go back to this sketch of system interacting with the environment. So the bath should be in equilibrium to let the system, which one couples to it, have the possibility to reach equilibrium with the environment. This is one of the conditions that you have to fulfill in a formulation of a system coupled to an environment for which you want to follow its evolution. Another condition is that only conservative forces have to be applied on the system. So conservative forces, I mean forces that derive from a potential with this gradient of the potential form. And then, okay, you have a situation in which either your initial conditions are already taken from equilibrium and you let the system evolve in equilibrium, in interaction with a bath which is itself in equilibrium under conservative forces, and then it will remain in equilibrium. This can be proven. I can tell you how you can prove it tomorrow or the day after tomorrow. Um, and then, if this is the case, then over time, the probability distribution of your system will be of the Boltzmann form, which I'm recalling here, with the h on top of the exponential, with kinetic and potential energy. And the potential energy is the one that you have here in the force. I show you two more results, and then I will stop because I see that there are some messages appearing in the chat, so probably there are some questions. So let me recall or introduce two properties of the temporal averages of observables of systems which evolve in equilibrium. So the first property, which is important, is that what we call usually one-time quantities, so the observable of your choice, call it A, depends on the phase space variables, but you measure it at the single time t, you average. These observable should be time independent. So with this prescription of averaging over a time window, so you take your time window around the time t, and whatever is this time t, if your system is in equilibrium, then the result should be independent on when you measure this observable. So one-time quantities should be time independent. So if you have, for example, a problem evolving with the Langevin equation, because you have gone from Newton to Langevin by integrating away the environment, this average here could be the average over thermal noise, for example, and initial conditions, or it could be the average over this time window with this prescription that I introduced in one of the first slides when I talked about time averages. Another property of equilibrium dynamics is that if you measure correlations between observables measured at different times, like here in this equation here, you have, the observable measured at time t1, then at time t2, then at time t3, and you correlate these observables. These should be translational invariant over time. So by this, I mean that if I translate all these times by the same amount, delta, then the result should be independent of delta. So for example, if you have only two time correlations measured, which usually we call with a C, we note with a C, and you call the two times T1 and T2 T and TW, like in my previous transparency, let me go back here, so T weighting and T, the two times over evolution, then this correlation can only depend on the difference between these two times, because you see if I translate T by delta and T weighting by delta, the delta cancel. So these are two important properties of equilibrium dynamics. If one of the two is violated, then you're sure you're not in equilibrium. If you measure and you see these two properties being validated, you're not yet sure that you are in equilibrium, but it's an indication. Okay, it goes in the good direction. You are in a steady state or a stationary state. These are the ways in which these things are called. But you're not sure that this steady state or stationary state is one of equilibrium. Could be of a different kind still. There are other properties of equilibrium dynamics, which I will discuss later in my talks, which should also be verified to be sure that you are in, Gibbs-Boltzmann kind of equilibrium. So maybe it's a good moment here. Let me see. Yeah, it's a very good moment here to stop and take questions if they are. I haven't read the chat. Let me see if I can read it. Somebody is saying that it seems we are not allowed to unmute ourselves.
Now that's enabled.
Okay. Will the slides be available later? I guess so. I mean, I can send you the slides after the talk, no problem. Why we have extra dimensions needed in classical mechanics for finding partition function? I'm not sure what I'm not sure of understanding the question. So what do you mean, Ananya, by extra dimensions?
In case of ma'am, when we are considering the quantum system, the partition function is z equals to e to the power minus beta h, and for classical system there is d into d plus 1 diameter we needed. So that's there I don't understand it properly. Why we need an extra parameter for
Okay.
finding?
Yes, so yeah, now I understand your question. This is a little bit technical, but I can give you the idea of why you need this extra dimension. So imagine that you are in the quantum mechanical situation. So the partition function is the trace of it to the minus beta h hat. So h hat is an operator, and the trace is over the um, Hilbert space of your problem, right? And the v-dimensional system that you have, I'm sketching here with a one-dimensional segment of length L, but okay, this L could be d-dimensional for a high-dimensional system. Now, the trick of Feynman Hibbs or Feynman himself was to rewrite this trace with a partition function, with a an integrable a path integral formulation in which this trace here is traded by the integration over an extra space dimension, which is actually a time direction. Uh, and on top of that, this time direction is periodic because of this trace property here. So you have to start from one state and go back to the same one because of the trace, right? So the trick is that you rewrite this operational trace that you have as a path integral, and then the trace is traded by or for an integration over this extra time. But okay, you have to see the calculation to see it, at work. So this is just a sketch, but you can see it in the Feynman Hibbs book, for example.
Okay, ma'am.
So in condensed matter, this is usually called the Matsubara or the Trotter-Suzuki trick. But in field theory, it's more attributed to Feynman, and actually it's Feynman who did it first. So there is another question about can we calculate the equilibrium time theoretically? So this is very difficult. So I will give you some arguments for example, the coarsening problems tomorrow. So to tell you how this equilibration time should scale with the system size. So there you can argue in different ways and get estimates. But to calculate it, to give you a formula, mathematical exact expression, it's very difficult, and it's only in very, very simple cases that can be done. And this is the sort of things that mathematical physicists were focusing on. The ones interested in ergodic theory were trying to derive, but for very, very simple problems. Otherwise, it's not possible to calculate it analytically. Does it really depend whether I will go to equilibrium or not on the initial configurations? Yes, it does depend. So I will give you again examples tomorrow or even later here where you can see it very, very clearly. So for example, you can imagine that if you start from initial conditions which are not very far away, one has to quantify what far away means, but okay, let's just say it, in a naive or intuitive way. If you're not very far away from the equilibrium that the system would like to reach under the conditions of the time evolution, then okay, you will reach it quickly. But if you are very far away, then you can remain out of equilibrium for very long. So it does depend on the initial conditions. What is the interaction contribution to Hamiltonian? It depends on the problem. I will give you examples. So, it depends. You have, I don't know, interactions within the system. You can think about, particles interacting with some two-body potential, for example, and then this will be the interactions. When you model the interaction between your system and the environment, for example, if you want to, there is a nice way, and this is a nice exercise that I suggest all the students to do in my lectures, and I can also suggest you to do it and give you some references to follow the calculation or to see how the calculation goes. is to derive the Langevin equation from Newton's equations. It's a very nice calculation. And basically what you do is you propose a coupling between system and environment, which is bilinear. So this allows you to do the calculations. So for example, if you have coordinates of the particles in your system and coordinates of the particles in your bath, you couple, say, the x to the q's in a bilinear form. And then to be able to integrate away the evolution of the bath, you propose that the bath is just harmonic oscillators. So then you have a quadratic equation for the evolution of the variables in the bath. You can integrate them away, and you can see how your deterministic Newton's equations for the whole system can become Langevin equations for your system of interest, the one you focus on, when you integrate away the environmental degrees of freedom, and you propose initial conditions for those environmental degrees of freedom distributed in some statistical way. So the statistical nature of the Langevin equation, or the stochastic nature, better said, of the Langevin equation comes from assumptions on the initial conditions of the environmental degrees of freedom. And this is very, I think it's very instructive to see this way of deriving the Langevin equation systematically. And it's also very useful in quantum systems where people have, systems in contact, and then you have to get rid of part of it, and you can get reduced descriptions of your system of interest. So interactions can be of very different kinds. Then it depends on the problem, the ones that you have to pick. Will you please explain about stationary correlation? Okay, I will. Yes, I will give you some examples later on. So I will, maybe in the examples, those will be clear. And well, tomorrow when I will be able to write on my slides, I will draw some sketches that will make that property much clearer, I think, than just in the equations. Yeah, can you elaborate on one-time quantities? This is just, an instant. Maybe you average over a time window around that instant, but you don't compare to what's going on at a much longer or different time from the instant you're measuring at. So, I don't know, imagine you have a magnetic system. You're an experimentalist. You have a magnetic system. You follow it with your experimental apparatus, and then at a certain time, you measure the magnetization. So you will get a number, only one. Okay, you have to average somehow to get a better idea than just one number that would fluctuate very much. So this single number doesn't tell you much. So what you want to do is you want to look at this magnetization around the time on which you're interested in, measure several of these magnetizations, and then you average over all of those. So you do a time average over a time window, but locate it around the time at which you want to measure. So this is just one time observable. So again, I have some sketches later on that may make this concept clearer, I hope. How can we average over thermal noise? Well, if you have Langevin equation analytically, you average over the thermal noise, over the noise in your equation. I will introduce the Langevin equation later in the slides, and you will see what I mean by this. So you average over that noise analytically or in the computer.
How can we actually account for what quantities come in this thermal noise?
Which quantities come in this thermal noise?
Yeah.
Okay, so let me move a little bit further in my transparencies. I have the example of the this is the example of Brownian motion. Okay, so what is Brownian motion? So you have some colloidal particle, so a big object, rather big object, that you put in water, for example. Okay, so this was Brown. What he was doing, the particle was pollen, and he was putting this pollen in water, And he was seeing that the pollen was moving in some jerky way, random kind of motion. The pollen was not following nice straight lines nor regular trajectories, but it was moving sort of randomly. So why so? It was interaction between the pollen, the colloidal particle, let's say, the green objects here, which are big in my sketch, with the molecules in water. So what we understand now is that these colloidal particles are, feeling collisions with these much smaller molecular agents, constituents of the liquid in which the colloidal particles are immersed. So if you want to do the Newton dynamics analysis of this problem, what you have to do is you have to write the Newton equations for the green particles, you have to write the Newton equations for the molecules, you have to write, follow the trajectories of all of these and see how they collide and, do all this. This is a mess, of course, because you have loads of particles in the liquid and you cannot solve all these Newton equations coupled together in this way. So what Langevin, Einstein, at the time did was to write kind of effective descriptions of this problem. And the Langevin in particular, what he did was to model in an effective way the effect of all these collisions by adding to the Newton equation a force which is random. And this random force, which is this thermal noise, represents the collisions of the particles of the environment with the selected system, which are the colloids, and makes them move in some sort of random way. He also realized that it was not enough to just add this thermal noise, that you also had to add some friction, that the fluid was also exerting some friction on the colloids. So he also added a friction term to this Newton equation. So in a phenomenological way, he wrote an equation which was just, m times the acceleration equals to the force. There was no external force acting on the pollen, so the external force was zero, but there were forces due to the interaction with the environment that were acting on the colloids. And these forces were of frictional kind, but also of random stochastic kind. And this is the thermal noise I'm talking about in this particular example. In other examples can be of different origin. But it's always, the interaction of your system of interest with the environment. And the environment here is the fluid. It's very easy to identify. In other cases, it might be more difficult to identify, but you can also model it in some rather simple or in as simple as possible way and try to get rid of it and derive these frictional and these thermal noise forces. Okay, so how can you average over thermal noise? In the analytical calculation with the Langevin equations, you just average over the noise that you assume has some kind of statistical properties. I will make them precise in a second. In the experiment, it's like averaging over different realizations of the experiment. And then you're averaging over different noises, for example. Okay, so there is a question. Apart from checking if the average of A is equal to the time average of A, are there other ways of checking if the system at hand is ergodic? So yes, so as I said, okay, you have to check that the one-time observables are time independent and are given by the averages with the statistical measure that you suppose describes the situation of the problem at hand. You have to check that the time correlations like these ones here are stationary. In principle, you should check them all. All possible correlations you can construct should be stationary. Of course, I mean, it's very difficult to check them all, but at least, you have to identify which are the relevant ones that you have to check for stationarity. And there's another property which is very important, which I haven't listed here, but I will discuss later in my lectures, which is what is called the fluctuation dissipation theorem. And basically what it's telling you is how the system reacts to an external perturbation should be in a precise relation with how the system reacts to internal fluctuations. So it's, external to internal. If external is small, in the limit of, external perturbations going to zero, these two ways of reacting should be in a very special relation that involves the temperature of the environment, the beta, and also the temperature of the system if the system is in equilibrium. So, so there is this other condition, which I'm not discussing for the moment, but that should be checked, and it's more how to say it, it's more precise, or it's more delicate. It tells you more about the behavior of the system than just stationarity. So by this I mean that you can have systems which reach steady states, which satisfy that one-time observables are time independent, and then all correlation functions are stationary, but still are not in Boltzmann equilibrium because they violate the fluctuation dissipation theorem. So, okay, I will let you know more about this later in my class.
So, can I just quickly follow up? So, basically, the question is coming from a more practical point of view, right? So, in the experiment, we typically only measure the time average of any observable. And in a theoretical formulation, we typically calculate the ensemble average.
Yeah.
To really make some analysis of the experimental data, we have to know upfront that the ensemble average will be equal to the time average, right? So for most systems, we won't know that necessarily. So is there any other way of
that's
saying,
right.
Yeah.
That's right. So for most systems, you don't know it, but in many cases, well, the assumption is good enough because you know that okay, you expect and you check in certain cases that they both agree, but it's to prove it analytically, of course, it's very difficult.
Thanks. Yeah.
So let me see what happens if the system has long range interactions, plasmas indeed. Then there is no reason to expect ergodicity or even Boltzmann distribution, etc. And the classical ensembles are not necessarily equivalent. Exactly. Yes, absolutely true. So in systems, there is a long discussion and analysis of systems with long range interactions. And there's a big group, especially in Europe and Israel. So there's people in Firenze, Lyon, David Mukabel in Israel, who were very interested in the statistical mechanics descriptions of problems with long-range interactions. And what people usually do is that you assume that the microcanonical ensemble is correct. You calculate with the macrocanonical ensemble, and then if you want to derive the canonical ensemble from it, you can't. So this assumption that you have to, that the interactions between environment and system is short range so that you can drop the contribution to the Hamiltonian that comes from the interactions, you cannot make it. And then you cannot derive the canonical ensemble from the microcanonical one, but you can still say, okay, let me do calculations with the canonical and see what happens. And in many cases, they do still coincide, although you cannot justify the canonical from the microcanonical, apart from cases in which you are, apart from certain regions of energies in the microcanonical, where in the canonical you have work that has been developed by Stefano Ruffo, Thierry d'Auxois, David Mukabel, Hugo Touchet, who I think is going to give lectures in the school as well, so most probably he will talk about this. So I will not discuss it, but I guess that Hugo perhaps he will do it. So, but you are absolutely right about the inequivalence of ensembles is the big name of the field, and there has been many people working on that, and also people in gravitation are interested in or people in plasma, as you say, as well. Yeah. Is the waiting time unique, or it can be chosen arbitrarily? So, okay, when you're doing an experiment or a numerical calculation, you select a waiting time, you choose it, and then you measure, and then you see whether you are beyond the calibration time in the sense of verifying stationarity and these properties here, or not. So it's like a parameter of your measurement. And then, you have to keep in mind that perhaps your results will depend on this waiting time when you are out of equilibrium. If you are in a steady state, the waiting time dependence will eventually disappear because things depend on time differences. So if you measure between T1 and T2, and you measure between T3 and T4, and the distances between T1 and T2 and T3 and T4 are the same, then it doesn't. Your result will not depend on T1 and T3. It will only depend on the differences between the times. So, in out of equilibrium situations, I will give you examples. Your results will depend on the waiting. In steady states, they will not.
Hi, Leticia. I mean, since there are a large number of questions, if you want, we can discuss this in the tutorials.
Okay. Yes, okay. I haven't. Yeah, okay.
Yeah, and then we can get back if they are not resolved.
Okay, good. Yes, okay, I will go on. Okay, let me close this thing here. Let me check the time. Of course, I'm late, but it doesn't matter. I mean, I can. It's good to have questions. It means that people are following and that they're not bored, or maybe they are bored. But anyway, okay. So how can you stay out of equilibrium? So there are 3 cases which I want to try to discuss. One is that the equilibration time becomes so long that it goes beyond any measuring time that you can reach in your experiment or numerical simulation. Another one is that you have forces that don't derive from a potential and you have energy injection in your system. And the third one is these integrability situations where you have so many constants of motion in your problem that the system is so much constrained by all these constants of motion that maybe you cannot reach equilibrium either. So this is a problem that arises, as I said, in quantum physics, but can be asked in the same way and studied in a very similar way in classical mechanics as well. So let me give you examples of the first one. So I already talked about Brownian motion. You know this problem. It's a canonical setting. It's the particles coupled to the environment. And actually, although this is not said in this way usually in the literature, this problem is out of equilibrium. So why so? Okay, I have my Langevin equation here. So this is, mass times acceleration. This is the friction I was talking about. And this is the noise that Langevin proposed. And I suggest you to read Langevin's paper. It's super easy to read and it's modern in its writing and it's very short and very nice. So he justifies the 2 forces in a very simple way. So you have thermal noise, you have friction. You have dissipation because of this friction term. So if you look at what happens with the energy of your particle, which only has kinetic energy because there is no external force acting on it, you will see that it's not conserved because of this. It's decaying the energy density of the problem. What about the noise? So the noise, you postulate, or Langevin postulates, that for this problem is a random variable taken from a Gaussian probability distribution at each time, and that the average of this random variable is 0, average over this Gaussian probability distribution, and that the correlation between this noise at different times is delta correlated. So there is no correlation between different noises measured at different times. And the prefactor here, and Langevin explains why, cannot be just anything to describe a bath in equilibrium. So to describe a bath in equilibrium at temperature T, this prefactor here has to be equal to twice gamma naught, so the friction coefficient, times kBT. So kBT, well, kB is Boltzmann constant, T is temperature. So if you use a bath of this kind, you will see that the evolution of these dynamics, whatever the initial condition you give to the velocity of the particle, will reach in the long time limit, the velocity, equipartition situation where you have that this mv squared that you have here in the course of time will approach kBt. So equipartition is a half mv squared, average over the noise, equals to kBt over 2. Okay, without the 2's, this thing should be equal to kBt. By choosing this prefactor here, Langevin shows that whatever the initial condition, this kinetic energy reaches this limit. So the velocities reach the equilibrium situation you expect with this choice of time evolution for the velocity. But now you can say, okay, let me not just focus on the velocities. If I have a particle, I have a phase space variable, which is position and velocity. Velocities reach what I expect in equilibrium, but what happens with the positions? So if you look at the positions and just, A here, okay, it's an index that labels dimensional, the directions in real space. So can go from 1 to D. So this is why I have an A here and I have a delta AB, but okay, if you can think about the same problem in a one-dimensional line or axis, to simplify the notations. Then let's look at X. What happens with the coordinate of this problem. So since there is no confining potential in this problem, imagine that your box is so large, it's a full world. There is no confining potential. There are no forces acting on the problem. And if you compute what happens with the position squared, average over the noise, this is a very simple calculation that I suggest also for you to do. You will see that this squared, average over the noise, does not reach a constant. Actually, it reaches a linear dependence on time with a prefactor here, which is usually called the diffusion constant, which depends on temperature and the friction coefficient in this way. But the important thing for what I want to stress here is that there is this linear time dependence. So this never reaches a constant. It's always increasing in time. And this is what is usually called normal diffusion. And the reason for there being normal diffusion and never reaching a constant value of this X squared average is that the system remains out of equilibrium because there is no confining potential. If there were a V of X, say, for example, a parabolic form, if there were a potential confining the particle with a parabolic form, you can also solve this problem. And you will see that the presence of this force here, extra force, which will be linear in X, will ensure that this X squared average over the noise will reach a constant in that case, determined by the width of this potential. But if you don't have a potential, it doesn't. And this is just, the simplest possible example where you have a problem which doesn't reach equilibrium. It's super simple. It's just Brownian motion or, diffusion, normal diffusion. So the particle is out of equilibrium. There is something else that can be said about this problem, which is very interesting, which is that you have coexistence of two variables in your phase space. You have velocity, which reaches equilibrium and reaches the Maxwell distribution of, equilibrium, which is e to the minus beta times the kinetic energy. And you have the position, which doesn't have a e to the minus beta v because there is no v. V is 0. So you have a 1 here, and the 1 is not normalizable if your system size goes to infinity. So without confining potential or without a finite size box within which your particle will move, the particle remains out of equilibrium. Simplest possible example. Let me see the, okay, but A single particle is not very interesting. You can say lots of things about this. Satya Majumdar is, the master of solving these kind of problems in different situations, and saying with Greg as well, so many nice things about it. But we want to go to macroscopic systems. We want to go to systems where you have a large number of particles in interaction, and in the large n limit, thermodynamic limit, say something about their evolution. So the examples I want to deal with are ordering processes, domain growth, phase separation. Systems with frustrated interactions I will not touch upon, but there are many nice examples one can deal with, especially spin-ices, frustrated magnetism, and so on and so forth. Then, okay, depending on time, I will say many things about problems with quench randomness. All of these are cases that remain out of equilibrium because the equilibration time goes to infinity under rather generic conditions in the large n limit. So phase separation, this is again a simple problem to visualize. So imagine that you have a mixture of water and oil that you prepare, for example, at very high temperature. So the mixture is very mixed. So you have, little droplets of both components, and they are completely mixed. And if you take a picture of your system and say that red is oil and white is water, they will be very homogeneous, and the droplets will be very small, and everything will be very mixed, as in this picture on the left, which I'm just signaling here. Now imagine that from this very high temperature initial condition, you cool your problem. Just a second. Yeah. Okay. So you just lower your temperature very quickly. This is what is called a quench. So you perform a rapid instantaneous quench, and you take your problem below the binodal, where actually water and oil want to separate. They want to phase separate. And okay, this is the phase diagram of this problem. So you take it through this critical point here, and here below, they would like to phase separate. So in the course of time, what you will see is that the red and the white regions will start growing in size. So locally, in different places, you will have red or white. And as time goes on, these regions will grow in size. So this is what these pictures are showing here. So here they're very mixed initial condition of high temperature, then you cool it down, then they start separating, and the regions of red and white continue to grow. So what I will argue tomorrow in my lecture is that one can estimate for this problem how the linear size of these red and white regions grow in time measured from the quench, from the moment when you cool down your sample below the binodal. And for these problems, although you cannot prove it analytically, you can argue, and it's rather well established that this is the way this goes. This typical length of these patches, of these domains, grows like a power law with t to the 1 over z. C is like it's not a critical exponent, it's an exponent, which takes different values depending on the universality classes of this problem. I will say more about this tomorrow. But anyhow, you can argue that these linear lengths grow like t to the 1 over z. Now, notice that to achieve full separation between red and white, say that you have half and half of water and oil. So to reach a situation in which you have, a slab of half size being red and another one of half size of the full system being white, this R has to be of the order of the system size, has to be L over 2, say. So if you equate this t to the 1 over z to L and you invert, you will see that this time that I'm now calling equilibration time goes like L to the z. So it diverges when L goes to infinity. So this evolution will not reach equilibrium in times that don't grow with system size as this power law. So if you're an experimentalist and you look at times which are shorter than this equilibration time, you will always see this mixture of red and white, taking some forms like here, but you will not see half and half. So equilibration time diverges with system size in these kind of problems. You can tell that the system is out of equilibrium because you have these remanent interfaces all along the evolution. Now you see here you have many interfaces, here have a bit less interfaces, here have a bit less interfaces, but you still have interfaces. So you still have this bubble of red or this bubble of white immersed in the surroundings of the opposite color. So this is telling you by just visual inspection that the system is still far from equilibrium because it's not just one single interface between the two regions. I said that this Z was like a not critical, but it was an exponent. And actually, in these kind of problems, which qualitatively we understand rather well, there are universal properties, and there are dynamic universality classes that can be defined according to how this typical length grows with time. And this will be subject of my lecture tomorrow. There are loads of realizations of this phase ordering kinetic sort of dynamics. These are not fast processes, they're very slow processes, what the systems are undergoing in time. Can we simply forget about the transient before this equilibration time? No, we cannot, because this is actually what's really happening in the evolution of these problems. So, okay, we can jump over this slide. There is not much more information. There is this interface local curvature driven dynamics, which I will discuss more about tomorrow. The interfaces in my previous slide were a realization or an example of what are called topological defects. There are other cases in which there are more interesting topological defects, which people like to understand in the context of statistical physics, also gravitation, also quantum realizations and so on. One such example is the case of vortices. So if you have a problem of 2D XY model kind, or a field theory with O2 symmetry, I will say more about this. They are like special points in the system which locate the presence of vortices. And in the course of time, what the system would like to do, as before eliminating interfaces, it would like to eliminate these vortices. And for these kind of problems, the equilibration times are not just power laws, but they are power laws with logarithmic corrections. And there's a lot of activity around this, especially experimental activity in the last years in the quantum context, but okay, you also have classical realizations. Quench randomness, what is it? So it's problems in which you have certain variables which are frozen in time and have an effect on other ones. So I will say more about this, but imagine that you have impurities. Let me see. No, I don't have it here. So you have, say, a magnetic system, and for some reason, certain magnetic impurities in this system cannot move. They are located, somewhere in the sample, and they point in frozen directions, let's say. So they exert magnetic fields on the other magnetic variables that you may have in your problem that feel the effect of these magnetic fields. And these magnetic fields, due to these impurities that are frozen in time, because the relaxation time is so long that it will never let them flip during the experimental time at which you're looking at your problem. So these exert, special effects on the other ones, and these are the effects of quench randomness or quench disorder. Quench here because it doesn't flip. There are different ways in which the word quenched is used sometimes, and this may cause a little bit of confusion, but so I will try to be careful and say it in detail. So this will be the discussion of the third lecture. Something that you may have heard about is that these quench randomness usually induce rugged free energy landscapes, so situations in which you go much way beyond Ginsburg-Landau way of thinking, and where you have a lot of degrees of freedom and a lot of all the parameters that you have to take care of, and the free energy density on those spaces of many all the parameters look like Hamiltonian ridges and hills and valleys and so on and so forth. I will say more about this. This is a problem that has an influence in optimization. So this is why it's also very popular in the computer science community and the applied math community to say something about these landscapes in concrete examples. And now it's also fashionable in the string theory. So you see the breadth of application of these kind of things are covering the full physics in a sense. Okay, I will go a little bit fast about this. I will jump over this now because it's a bit late and it's not really necessary. So, okay, let me jump over all this. Now, let me show you the examples where you have injection of energy. So these are what we call driven systems. So they're non-potential forces acting on the system, which make the energy not be conserved. So how can you do it? In different ways. So one of the situations is where you couple, say, your system, this is the H system you focus on, and you couple it to reservoirs or environments, surroundings, which are at different temperatures or with different chemical potentials. And then, if you have different temperatures of these environments, there will be energy transport from one to the other one through the system. So, the system will feel this energy transport through it. Or if you have different chemical potentials, you will have transport of particles through the system. And then, okay, you will see the current of the particles going through the system. You can even have external forces acting in time in different ways. So you can force your system with some sinusoidal wave, for example, and then your force depends on time, and then you're also doing something on the system. So there are many different ways in which you can inject energy from the outside world. And typically, these realizations I'm talking about here, the energy injection occurs through the borders. So here you have the system, and through the edges, like right and left, you inject particles, energy, or whatever. There are also situations which are much realized experimentally in soft condensed matter, for example, where you do rheology. So you put your liquid or your soft condensed matter system within a hole with two cylinders, a different diameter. You put it in the middle, you turn one in one direction, the other one in the other direction, and you see how the system reacts to that. This is the torsion kind of experiments which are sketched here on the left. And then you are also injecting energy by doing this kind of mechanism on your problem, and you want to see how the system reacts. So these are the kind of traditional ways of injecting energy externally on your problems. And then you can see, how this drive that you're doing alters the transport or influences the transport properties of your problems, and there are loads of literature on that. Let me jump over this. Yes, I will. Now let me go to this example, which is one which I would like to discuss in one of the lectures, and which is very fashionable nowadays, and many people are working on this. So this is what is called active matter. Active matter is composed, let me read here, composed of a large number of active agents, particles. You will see examples. There are many realizations of very different sizes, so different scales. But now the energy injection occurs within the sample. So each of these agents is consuming energy from some motor or some environment that locally is giving energy to it. And these agents are using this energy to move or to exert mechanical forces. This typically in cellular applications of these kind of ideas, the mechanical forcing aspect appears. But then, because of this energy consumption, these systems are really out of equilibrium, very much so, very far away from equilibrium. So energy injection is done uniformly within the sample and not from the borders, not like in the examples I discussed before. So this is a little bit different. And the systems just don't get all this energy and they start heating up, increasing their energy with no limits. They are also coupled to a bath. There are frictional forces that allow them to release part of this energy that they get from the motors, let's say, towards the bath. So there is energy injection, but there is also energy release into the environment. And there's this complex situation that arises. So let me give you examples. One of the examples which are very nice to show in pictures is this birds flocking situation where you have these birds which are moving in the sky and making very nice figures. So this is one of the areas in which these kind of ideas are applied. But then at a much smaller length scale, you have the case of bacteria, for example, which are these elongated animals, I would say, that interact between them because they are typically, in the dense situations like in this image, and they move and they do collective motion, and you want to try to understand this collective motion and say something about them with the statistical physics ideas, but out of equilibrium because they are consuming energy. You can even go smaller and work with artificial systems. So these are systems made of these Janus particles. So Janus particles are like spheres, but which have different sides. The red and the blue in the sketch are of different kinds, and these kinds chemically react, one of them typically, with the environment with which they are in contact. And by these chemical reactions, they are pushed in some direction. So imagine that it's the red that reacts with the environment, and this reaction makes it move in the left direction, let's say. But of course, if you have many of these, they are not only moving in straight lines, they are also colliding, and there are also interactions between them. And then you want to understand the collective motion of these and how they behave when they are in dense situations and so on and so forth. So these problems are also modeled with Langevin-like equations. So this is the standard model of these problems, which is called the active Brownian particles. So it's like the Brownian motion I mentioned before, but there is this extra ingredient of there being this active, usually called active force, acting in a particular direction. So in the example before, it would be this direction here. But of course, this direction can rotate because of the interactions with the other ones or because of the collisions. This particle can rotate, and the blue look towards the top of the slide later on, and so on and so forth. So in the model, there is not only this propulsion in this particular direction determined by this vector n here, but there's also the rotation of this direction, which undergoes Brownian motion, angular Brownian motion, with a different noise, eta, which is here. So I is the index of the particle, theta is the angle of this particular direction, red from blue, but this is rotating because of collisions, because of thermal noise, because of many things. So here you have this noise acting on the angular direction. And then you have the interactions between the particles, which is typically just purely repulsive. So this is the potential is of repulsive kind. I will define it later on. You also have a translational white noise, like in the usual Langevin dynamics. Then you have the friction, and typically you can drop the inertia term. So typically you can go to an overdamped limit where this MV dot can be neglected, but you can keep it if you want. So this is just a generalized Langevin equation where you have this active force also acting on the particles. I will define the control parameters in my lecture on active matter. One is density, basically, and the other one has to do with how strong this active force is. So this activity, what it does is that it changes the random motion of the particles with respect to just normal Brownian motion, and it induces persistency in the displacements of the particles. So they tend to go longer in given directions before they rotate. So these are typical examples of some simulations where here you have the particle without activity and here you have the particle with activity, and the other ones, they are there, they are in interaction with the red ones, but you see that the motion here is much more persistent than there. Okay, I'll jump over this. It will come to when I'll talk about activity. Last example in the 5 minutes I have is this integrability. Okay, let me just show you the motivation. So as I said, the quantum people are able to do experiments in rather good isolation. And for example, what this group, which was published a very influential paper like 15 years ago, what they did is I prepared an ensemble of atoms in a rather parabolic trap, like it's a sketch here. So they prepare these atoms at the bottom of this trap, and then they split the cloud and they let it move in some way. They pushed it towards the outside, away from the minimum, and then they let it evolve. And what they saw is that this cloud was doing this periodic motion. It was not destroying, it was going back and forth, like deterministic motion. So this was in perfect isolation. It was kind of they call it the quantum Newton's cradle experiment, because it's similar to this toy where you have these balls that move back and forth and they stay like this for very, 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 very long. So this problem doesn't dissipate energy and doesn't destroy this situation for very, very long times, experimental times. And then people realized that they could reproduce this situation in different ways with, either numerical simulations of quantum models or even exact calculations of certain simplified quantum models, and that this behavior had to do with integrability properties, all these constants of motions which are conserved. And there's a lot of activity in the quantum realm on this kind of questions and issues. And the issues that people ask is that, okay, there is all these conservation laws, but perhaps if we look at certain observables, then we can describe them with some statistical measures or density matrices in the quantum problem of Boltzmann kind, or maybe extensions of the Boltzmann kind. And these extensions are, what are called generalized Gibbs ensembles nowadays, and that can also be found in classical systems. So if I have time, I will talk about them in the last lecture. Okay, let me jump over this because it's late. We'll tell you about this later on. So just let me finish with the purposes. So the purposes of my lecture will be to go a little bit deeper in these 4 examples. So this is the coarsening example. I will tell you much more about them tomorrow. This is just a sketch of the effects of Quench randomness seen from the point of view of the free energy landscapes, but I will explain how you derive these in simplified models in the 3rd lecture. Then this is an example of what these active particles do. These colors have a meaning. Not only is a nice picture, I will try to explain these to you as well in the 3rd lecture. And then, okay, this is a sketch of the kind of procedures that the quantum people do, putting particles in different potentials that they create with lasers. Then they change the potentials and they do what they call a quantum quench. And they try to see what happens with the evolution of those particles under this quench. So if I have time, each lecture will treat each one of these subjects. Hopefully not too technically, because it would be impossible to do it. It would need, each of them a full set of lectures. But just to give you a flavor of what are the issues, the problems, and the questions that we ask. So thank you for the attention, and now I can answer questions if you wish. I mean, I don't know what's the idea, if to stop sharp at 8 for me, or I can answer the questions now if you wish.
Yeah, if you have some time, I mean, if you you could answer, I guess, but or we could take them tomorrow. Like after the maybe after the tutorial, maybe some of this will get cleared, and then we can ask tomorrow. I mean, if you think you want to answer some urgent question, you could.
Okay, let me check the questions. I haven't read them, so let me see where I was. The Brownian motion in grand canonical setting. Yeah, I guess that there is ways to do it. I don't know. I should think about it. I mean, to check if I know of a reference for that. I'm not sure. So that one I will check. Earlier you said that regression time can depend on the initial conditions. Is it possible to speed up the process? Yes, it is. Yes. This is one of the issues about optimization, indeed. So what you want to do is to try to reach equilibrium as fast as possible, and then try to find smart algorithms to do it. But yeah, sometimes it's a difficult question, sometimes it's easy. So I will let you know a little bit about this tomorrow. Yeah. During phase separation, why is it required to have one single interface between phase to stay in equilibrium? Well, this is the configuration with the lowest possible energy. So, the excess energy is between the nearby particles, which are of different kind, no? Because there is where you pay something for. Otherwise, the particles, they are happy to be with their own kind. So you want to minimize the interface, and this is why the way of minimizing the interface is just for half and half systems. They say it's just to have a flat interface between the two sectors. What if there are more than two phases? Yes, you can have phase separation in POTS models, for example, which have many different equilibrium phases, and then you want to separate the colors of the POTS kinds. So yeah, you can also do it. If a separation does always interface between different compositions disappear, or can they also appear during evolution? Yes, they can. They can appear. I will show you some examples tomorrow. So because of thermal fluctuations, you can let fluctuations of the other kind appear within the domain of the majority, let's say. But this depends on the microscopic dynamics that you have. So I will say more about this tomorrow. What is the difference between color noise and white noise? It's the correlations that you have in the noise-noise correlations in time. So if you have delta correlations between the two noises measured at different times, this is white noise. If you have not delta, but just some functional form for the correlation between the noises at two times, this is what is called color noise. And the reason is because if you do the Fourier transform, in the white you have flat, in the color you have some structure in frequency space. Rotational noise Gaussian as well, apart from being white noise. In the usual models, yes, we take it to be Gaussian as well, the rotational noise. But you can think about different things, different choices. But yeah. So there is Prashant here who's raising a hand.
Prashant, just unmute yourself and ask.
It's not violation of detailed balance, which is the problem in the integrable systems, because in the example I will give you, the dynamics is Newtonian. So, you're not breaking detailed balance. But what you cannot do is to go from the macrocanonical. Actually, the macrocanonical distribution for these integrable classical systems, you can prove it holds. So there is a very nice paper that I can give you the reference, which discusses this, published in Annals of Physics like 3 years ago. So the macrocanonical is okay. The thing is that when you want to derive the canonical one, you cannot really do it because you have, there are so many constants of motion that you have to take care of that, you cannot argue for this, that you have that you separate the system and environment and this and that. So this is the part that fails. But then in certain cases it does hold anyhow, and you have an extension of the canonical weight where you have in the exponential all the let me see if I wrote it, all the constants of motion appearing. Yes, here it is. So you see, well, I wrote it in quantum notation, but it's the same in the classical one. So this is just the extension of the canonical weight, e to the minus beta h. But here you have to put all the constants of motion. So these I mu's are all of them, and the gamma mu's are like Lagrange multipliers imposing the that the statistical average of these constants of motion be equal to the initial values of those constants of motion that anyhow are conserved. So although you cannot derive this from the microcanonical ensemble, in the example I will give you, this measure describes the behavior of the local observables. Local in the sense of system with respect to bath. So yeah, there are many issues to be understood in this milieu. I mean, this is in a way it's a starting. In the quantum, there are many papers, but typically they are applying to one-dimensional chains and one-dimensional systems, which are particularly simple. And now there are some, tougher analysis of interacting quantum problems, but in the classical, there's not much done. So I think there's a lot to be done here.
Thank you.
Hi. You're welcome. Yeah. So
Hi. Yeah, I have one very specific question. Suppose I consider a classical many particle interacting system described by a Hamiltonian, and let's say I sort of write down equations of motion and I couple different particles to some Langevin baths at same temperature. So is it guaranteed that there is a unique asymptotic stationary state, which is a Boltzmann distribution given by the same Hamiltonian? Is it always guaranteed?
For a problem involving Langevin dynamics,
yes.
and with a Hamiltonian which has a gap, sorry,
yes.
which has a gap, yes, yeah, you can prove it. You can go from Langevin to Fokker-Planck, at least for white noise, you can prove it easily. So if you have white noise, you can derive the Fokker-Planck equation, and then you can, for example, use the mapping of Fokker-Planck to Schrödinger. And if you have a gap, then the ground state of the Schrödinger is the Boltzmann distribution, basically. So that you can, I mean, it's related to Boltzmann distribution, and then when you go back to the Fokker-Planck formulation, you see it corresponds to the Boltzmann distribution. So then you can prove it, yes. For color noise, it's more complicated because you cannot derive the Fokker-Planck equation for the color noise, and then then it's not so obvious, I think. But
so for the white noise case, does it matter like where I put this system in contact with the bath? Like maybe at a single point I put the system in contact with the bath. Does it guarantee that still my system reaches?
No, I was thinking about each variable being coupled to a bath. So if you start saying that you couple only locally, then you have to ensure that you have good transfer of everything within the system, and the effect of the bath that moves, and then I think it might be more difficult to prove. Yeah.
Leticia, I just had a question. Can I just ask?
Yes, sure.
Right. Yeah. So I mean, so there's a viewpoint among many like statistical physicists that what you need for StatMech to work is typically, and ergodicity is not so crucial, right? At least Joel Lebowitz has been saying this. I mean, all the while. So I mean, from the point of view of like what you said, does this mean that at least for some observables, you had a time TW and then you had a time tau? So maybe for some observables, this time tau is not so crucial. I mean, like it can be quite small compared really to the time it takes.
Yeah, indeed. I will show tomorrow, for example, with the example of the coarsening and domain growth, you will see that things are much more complicated. So there's not only you can have variables which equilibrate and variables which do not coexistent, like in the case of the Brownian motion, which is a trivial example, but there you see it very clearly. But in the coarsening, you can have situations where you look at correlation functions, and for short time differences, the system is as in if it were in equilibrium. So you correlate the configuration of your system at a given time t weighting, and at a given time t weighting plus tau, and tau is small, then everything behaves as if it were in equilibrium. But then if you go to longer times and you compare times which are farther away in the evolution, then you realize that the system was not in equilibrium because the interfaces basically start moving. You give time to the interfaces to move, and then you realize that the system was out of equilibrium because of the interfaces. But if you look at correlation functions, which are not letting the interfaces move, then it's like a patchwork of systems in equilibrium put together, and you don't realize the system is out of equilibrium. So there's one has to be careful about, once you are out of equilibrium, then there can be certain things which are in equilibrium within the out of equilibrium situation. Let's put it this way.
Okay. So at some point you'll discuss this dependence on observables or on like. Right.
Yeah, not only on observables and on timescales.
Right. Yeah.
Those are also going to be important. Yes. Okay. So I have to say that I'm very happy, because I got a lot of questions in the chat, and I'm very happy to not cover everything I thought I was going to cover, and answering the questions is much more interesting for me and for you, so as well. So keep asking questions, get many questions for tomorrow, and can start answering questions at the beginning, and then go on with my lecture later on, or just do it as you prefer. Mm-hmm.
Okay, so thanks. I think there are no other questions. So we meet again tomorrow at 10:30.
Okay, so thank you very much, and see you tomorrow then.
Yeah, bye.
Bye.